Welcome everyone, last talk of the day, of the conference. I'll try and keep us awake. Just to be clear, this is an introductory talk. It's really aimed at people who might be kind of new to some of these ideas. And I won't be offended if you're an expert and you want to go to a different talk, that's fine. We're going to be talking about extracting topics from text, and my aim is to really kind of help us to kind of understand what the algorithms are doing in an intuitive way, rather than do a session on linear algebra or anything like that. So if that's what you're interested in, we'll dive in. So we'll talk a little bit about text mining and in particular topics, what they actually are. We'll kind of cover some ideas around concepts and some maths. But as I say, it's really to develop the intuition and not to kind of do a session on sort of linear algebra and stuff like that, probably because I can't do it. And then we'll see the application later, applying it to some interesting data sets to see how that works. It's usual to kind of do a slide on who you are. It's usually very boring, so I thought I'd make it interesting. This is the picture they took of me on reception. So if you want to get in touch, I'm on Twitter as Post Enterprise. Don't know why I chose that name, but once you choose it, you can't change it. I help run the London Python meetup, so if you're interested in Python in general, come along to that. It's once a month. I've just started another meetup group on algorithmic art, so if you're interested in that, come along. And I've written a little guide on neural networks, which you may be interested in. Cool. So text mining. So the world is full of text. It's everywhere. People write blogs, people write books, reviews. There's evidence that police and other authorities collect. It's mostly text. We all email each other. There's piles of this stuff. We all write reports, and they all contain, and news, they all contain interesting things. There's just piles and piles of this stuff. And it would be really cool if we could, in an automated way, understand what was in that huge plethora of text. And anyone who could do this, anyone who could solve this problem, is going to be, pretty powerful. But that's the challenge, and it's a hard problem because how we talk and write in English and other human languages is messy, ambiguous. Our human languages aren't constructed to be as precise as computer programming languages. And that's the essential challenge of text analytics and text mining. We're working with data that doesn't really conform to precise rules. But there's still lots you can do despite that challenge. So just some fun examples, Maria saw the girl on the mountain with the telescope. Well, there's some ambiguity there. Who's got the telescope? This is a real headline. Squad helps dog bite victim. So these are joke examples, but they illustrate the point that human language is messy, ambiguous, not precise. Wasn't designed for computation. It's perhaps a better kind of illustration of the challenge. So if I sort of had a container with sort of three things in there, three numbers perhaps, 3.1, 3.2, and 11, so 117.9, and I said to you, show me the two that are most similar, and most of you would probably say these two. And if I said to you, well, why? You'd probably say, well, they're close in terms of some measure of distance. 3.1 is not that from 3.2. Or perhaps you might say 3.2 is much further from the bigger number. So we can understand that, we're comfortable with that. But if I said, can we do that with some words? Which of these words are most similar to each other? You would probably say apple and orange. But if I said to you, well, why? You start to then think about some of the challenge in codifying in a computer program your kind of thoughts around why apple and orange are similar. And it's not easy, but people have had kind of good attempts at trying to codify that. There's been lots of talks this conference already around a word by the company it keeps. So that's an example, the words that you might find around orange are probably the words that you find around apple, probably. And the words that are around these two probably aren't around the word cloud. So that gives you a lead. But if I sound kind of unsure, that's because it's not an exact science. So it's not an exact science, the data mining can feel a little bit like alchemy, a bit like voodoo. But having said that, despite the fact that it's a difficult non-analytic problem, we can still do some really useful things, like we can search inside text, we can find words that are similar by some definition of similar, like the one we've just talked about, and that's useful. So here's a question just to kind of get us thinking. If I plotted a word cloud, which is showing the most common words in a bunch of text, I might say to her, what's this text about? And you'd say, yeah, I think it's a bunch of recipes. Maybe if I look closer, it's Italian recipes. And that's useful. That's an example of data mining. And it's a simple example. I know people take the mickey out of word clouds, but they're actually simple and very effective. You didn't have to read the recipes to understand. You didn't have to read the text to understand the text was about recipes just by looking at that. So it is quite a powerful technique. That's an example of text mining. Another example is clustering together documents that are similar, and the measure of similarity here is they share common words. It might be a naive idea, but it works well enough. So here's some documents around the Iraq kind of report. Here's some Italian recipes. Here's some Clinton emails, and here's some Shakespeare's text from Macbeth. So that's a useful thing you can do. I actually find it quite interesting that if I plot more of the stuff together, you find that Macbeth's related to Iraq, maybe because they're both about blood and killing and stuff, which is kind of interesting to make you think, well, what's Clinton got to do with blood and killing and stuff? But it's interesting that recipes aren't very connected to those things. So those kind of ideas are quite common now, and they're useful. They're really insightful, as you've just seen. But clustering things together is useful, but it doesn't really answer one question, which is, what are the key themes or topics in a bunch of text? And that's what today's talk, I hope, is about. So what do I mean by topics? So if I had a bunch of text, maybe a pile of papers with some writing on it, and I said to you, look at this, there's some words. What are the topics in this pile of text? And I've color-coded them to make it easier. And you could look at that and say, actually, yeah, I can see there's two topics there. There's something around cooking, slice, oven, chop, boil. And maybe there's another topic around vehicles, cars. And that's exactly what we want to try and automate. We can separate those two topics out. That's what we want to do. But how do we do that? That's the objective. Can we automate that? That's really what we're trying to do. And if we could do it, it'd be really useful. I've been lucky enough to work in some parts of the public sector where, we've had investigations. The Hillsborough kind of evidence disclosure, or the inquiry into sort of child abuse, the Iraq kind of inquiry. There's a lot of textual evidence, and it would help if we could have a computer help and guide us through all that huge volume of text. I have to say, sadly, historically it hasn't been done very well. It's not been done very automated. I'm sure things will change. But that's, and if you work in finance, they're always sort of litigating against each other and producing sort of disclosures of evidence, and that can potentially be interesting as well. So let's just take a step sideways a little bit now and try and think about how we might solve that problem. As I say, just to stress, I'm not going to go through sort of proofs of mathematics or anything like that. I'm just trying to take a little journey which takes us from sort of simple ideas and helps us to intuitively understand how one of the methods works. So we have text, but in order to work with it, we have to think of it as data. So we have to structure it in some way. And most people would say, yeah, we've got documents, and inside documents is text. Kind of makes sense, yeah. And a very common way of encoding that is to build a data structure, a matrix, which shows you which words are in which documents, and you may have come across the term document matrix, and there's lots of things you can do with these, which is why they're popular. Just to illustrate that, the word boil appears in document 2 twice, but doesn't appear in this document. So I've misnumbered these things, so I'll correct that later. And I've color coded these so you can see the word slice appears quite a lot in that document. Wheel appears most in document 1. So what we want to do with all that information, which is the words in a document and their occurrences in some sense, that's a lot of information. It's particularly if you've got realistic data with thousands of words and lots of documents, we have to somehow reduce that into what we've called topics. We don't want thousands of topics. We want something that says, actually, we've taken all this data and distilled it down to a few things, a few themes. At a high level, that's what we want to do. Some of you may spark up and say, actually, that sounds like compression. If you're familiar with that side of computer science, you might say, that's the task. We're compressing and representing as best we can all that information with a lot less information. Yeah. So what could we do? We've got lots of data. We could throw a few kind of data points away at random. It's not, well, we could, but I'm not sure that would actually retain the most useful information. We could keep the biggest numbers. Yeah, that's probably getting warmer, but that's actually not too dissimilar to what we did right at the start with the word cloud. It'll give you the most frequently occurring words, but perhaps not the themes. Well, getting close. Maybe we can throw away some of the rows and columns of this thing. So as I said, this is a noddy small example, but realistic data sets would have, 19,000 documents with a vocabulary not of 6 words, but maybe 2,000 words. That's a big matrix. Maybe we chuck away some of the rows and columns and try and reduce that. Is that an approach? Maybe. So actually what we've just been doing is just throwing random ideas around. So instead of doing that, let's try and be a little bit more systematic and reasoned about how we do that. So take another sidestep away from the problem and say, let's just start with an idea, a mathematical idea. Imagine we have this matrix, this term document matrix. Actually, we want something smaller. So maybe I can break this down into 2 pieces that are mathematically related in some way. And if that works, that would be nice, wouldn't it? Because then some information might be encoded in here, which perhaps is useful and tells me useful things about the big matrix, but it's distilled and smaller. It's much more easily understood, perhaps. It's an idea. But actually, if you remember your school maths, multiplying matrices has some rules. So the number of columns here and the number of rows here have to match the number of columns rows here, which means these can't be any size. I can't just change this to any size. So that doesn't work. But let's not give up. Let's extend the idea a bit. Let's say we break it down into 3 matrices. And actually, this looks more promising because if we apply those rules again about how the columns and rows have to match up, you find that this number of columns here has to match this one here, the columns here. The rows here have to match the rows here. And this middle one can be any size. That's kind of magic. And that's really going to help us, actually. So if we could break our term document matrix down into 3 smaller ones, or similar size ones, or bigger ones, the fact that the middle matrix here could be any size could be useful. It might mean that we could make this bigger and smaller, and by making it smaller, we've in some way chopped out unnecessary information and still rebuild something that approximates the original data. And as it turns out, there is a mathematical approach that does just that. It's got a horrible name from, I don't know why mathematicians choose unfriendly names. It's called a singular value decomposition. And all it does, it takes a matrix and breaks it down into those 3 smaller matrices. And you know, this is just like, you know, taking a number 12 and chopping it up into 12 is 6 times 2 times 1, for example. Decomposition, they love their fancy words, don't they? And Python has this method. In fact, if you Google it, you'll find there's 2, or which is kind of frustrating. But the NumPy set of libraries has the SVD, and so does SciPy. And in fact, the underlying core code is the same, but one just provides a few more options, and you can Google that. In fact, I'm going to give you links to notebooks online which illustrate how to do it. So you'll see a really simple example that's worked through. So you can have a look at that afterwards. So just to kind of repeat and re-underline what we've said we're taking some data. This is a bitmap here which represents a face. We're decomposing it into those 3 things. Actually, I didn't talk about explaining that a little bit. Yeah, I should do that. So, you know, in simple terms, there's some nice features around this. So this mapping, this breaking down, this decomposition to 3 bits is kind of unique. I'll put a star there because it's unique enough for us. I think mathematically it's not quite, but you can read more about it at this link. It's good enough for us. This thing in the middle is really nice because it's a diagonal matrix, which means it's 0 everywhere except along the diagonals, and it's ordered so the biggest number is in the top left and the numbers get smaller, which is really nice and neat for us. It means that if we choose to change its size, we can chop out the small bits, and we kind of hope that means if we remove a small number, maybe we're chopping out the least significant bits of information. If you want to keep only the most significant bits of information, maybe we just keep the biggest kind of element of that matrix. There are some other bits, like the fact that these 2 are contain columns and rows which are orthonormal. Don't worry about that too much. You'll see how that's useful later. So just to illustrate that point again about reconstructing the data by changing the size of this middle one. When I say changing size, it means discarding some of the smaller elements of it. So if this is broken down into these 3, if we say let's just lose the smallest numbers and rebuild that original data by multiplying those 3 things again, you get a kind of a good approximation. And if I lose more of those smaller elements, you get a less good approximation, but it contains the main features. So that's kind of useful, because what it's saying to us is we can take data and we can have a smaller representation of it while keeping the most important features of that data, the features that give it the main shapes in that data. So this is just like compression. In fact, some people have done image compression. There's better ways of doing it, but it's an approach. So let's just talk a little bit more again, because this talk is meant to be about intuition. What's it doing? So if I said, here's a bunch of data, how would you describe this data if you only had one dimension to describe it? Well, you'd probably pick an axis along this direction, because it allows you to, it's the direction of the most variance. And if I give you the luxury of another dimension to describe the shape of the data, you might pick one that's kind of along the other direction. So with those 2 kind of dimensions, you've kind of approximated the data well enough. And actually, if you had more dimensions, maybe imagine this coming out of the screen at you, you'd have another axis that points towards you. And you can keep going on and refining how well you describe the data. But the important point is your early kind of selection of dimensions describe the main feature. So with our very first description, we didn't point in this direction because it wasn't the direction in which the data varies most. And that's really what that decomposition is doing. It's interesting that these things are in different directions. In fact, they're orthonormal when we do that breakdown. If you're wanting a more kind of mathematical kind of picture, each of those descriptions of the data are actually the best fit if you use the least squared distance that you can have when you limit yourself to 1, 2, 3, 4, 5 dimensions. So that's mathematically rigorous, and you can look that up if you want to. So if I looked at that middle sigma matrix, one with the diagonal numbers, if I plotted them and said, actually the top left 2 numbers were really large and the rest were small, well, what does that tell me? It tells me that the first 2 dimensions are the most significant in describing the shape, and the rest are just little refinements or perhaps noise. And this is a useful check when you are decomposing data to say, actually, how many dimensions do I really need to describe this data? And I'll probably say 2, maybe 3, but probably 2 is enough here. And that's a useful thing to be able to check to see what those numbers actually are in that descriptive matrix, the singular values in that diagonal matrix. But what's this got to do with text, which is what we're here for? So the kind of assumption here is that if we had text data, the assumption is that each of these directions describes the topic. That's the underlying assumption. I guess I have to think a little bit about why that's a good assumption. But I think part of it is that those topics are orthonormal, they're different, they're not clusters of similar things. It's sort of saying, along this direction, there is a theme of which the text either has a lot of or a little of. So let's see that applying to not an image, but the actual word term document matrix. So we're breaking it down, and if we take just these 2 multiplied together, what we're doing, if you remember your school maths around multiplying matrices, what we've done, if you look across here, remember it's the words. So the rows describe each word, the occurrences of the word in the document. So row-wise is a description of the word. And in this new view, in this new kind of land where we've transformed that data into, the same thing happens where we multiply rows of this U matrix by kind of a selective element here. It's row-like, it's word-like. That sounds woolly and shaky, so I'll talk a little bit about that. But if you didn't want to kind of get into the deep maths of it, you could say the rows of this thing are word-like, and the rows of this thing are word-like. Similarly, columns would be document-like. But I didn't really believe it when I first read about it, so I spent a while trying to kind of dig out some kind of proof of it, and I found a justification which convinced me. This actually is a reflection of the fact that this is all kind of, a lot of text mining is still a little bit kind of voodoo. None of it is kind of mathematically 100% grounded, in axioms. It's all a little bit based on assumptions, just like the bag of words model that you've heard a lot about. So let's kind of, if you're not interested in this, but you can close your eyes and take a rest. This is a diversion. But this is my justification of why U times that middle matrix is a new representation of those words. So we know that the matrix, the word document matrix, can be broken down into U, sigma, and VT. That's just a convention. If we say that if we multiply that thing by its transpose, it's if you shift it along its diagonal, what you get is a word-word correlation matrix, and if you write it out, you'll see why that's the case. It's not hard to see that. If I expand this thing out, and I haven't got time to totally dig into it, but it's very simple maths here, and I've explained the algebra, you end up with these quantities being the word correlation, and because those are the same, you can think of these as word-like. It's not mathematically the same as saying that the word document matrix is U times sigma, but they behave like that, and here's kind of a justification that the best one I could find. If you can find a better one, let me know. I spent weeks trying to find a justification. Anyway, back to text mining with topics. So what we've done, let's apply it. So earlier on we looked at a really simple set of documents with some 6 words, and we made a matrix with the word frequencies. What I've done here is actually normalize. So we've normalized by document length, because if you can imagine, long documents would unfairly get prominence. It'd be lots of the same word repeated. So this is a common thing to do. And if we break that down, A, into those 3 matrices, and then multiply these things together, and if we only keep the top 2 values, this is what we end up with. And these are the topics. So the first topic is made up of some combination of slice, oven and boil, and the second topic is made up of some combination of wheel, seat and engine. And that's right. That set of documents were about 2 different themes, and this is what they are. The first topic has nothing to do with wheel, seat or engine, and the second topic has nothing to do with slice, oven and boil. It's separated those out. That's kind of nice. You can look at the notebooks which are online to kind of explore yourself and have a play. Let's apply it to bigger data, because that was a small naughty example. So in 2012, government released 450,000 pages of evidence around the Hillsborough disaster. There's, from 85 organisations, there's about 19,000 text files. And if we apply kind of a pipeline, which you'll be familiar with a lot of this thing, we take the original text, we clean it a little bit by removing some of the multiple white spaces. We might keep only the alphanumeric characters, we might lowercase it, the standard things you would do to clean up textual data. And then we make the matrix. In fact, I've done something a little bit more sophisticated than the word count or the frequency. We've applied the TF-IDF, which you've heard about in some of the other talks here. It's simply saying that words that appear in every document, like the word the, aren't actually that interesting. So you give prominence to words that appear a lot in some documents, but penalize them if they appear everywhere. So term frequency boosts that score, but inverse document frequency penalizes it. So the word will appear everywhere. Again, you can read more about it with this link online. And then we do the decomposition of that matrix. My computer wasn't powerful enough to crunch through all of that, so in the end I applied another filter, which was just keep the English words, which might lose some interesting words. And this is the spectrum, as it were, of that middle matrix, which gives you an indication of, well, what are the most important dimensions. This is the full plot. It's a very long tail, but you can see that there's maybe 1, 2, 3, 4, maybe 5 dominant topics. And here is what they are. And if I look at them, well, what do I see? I see, well, some of the words are right. Talking about police, the material, the ground, the actions, the people. Something around sort of some of the inquiries that happened afterwards, like the Taylor inquiry. But if I'm honest, didn't work that well. Yeah. Okay. So back to the drawing board. I don't know why I love this, Jeff. Anyone know who it is? Exactly. Someone's going to say Doctor Who. That's because a lot of the original material was photocopies of handwritten notes, scanned and then OCR'd, and the extracted text looks like this. So you can understand why naively applying some cool library function doesn't give you great results. So this is just, I put this in here just to remind us that data, looking at your data and exploring it up front is really important actually. And actually, given that a lot of the data looks like this junk, it's surprising that it's kind of done that well. Let's try it on a cleaner data set. So the Iraq report was typed into a word processor, I imagine, rather than sort of bits of paper sort of many years ago. And this thing's got 2.7 million words. By the way, I'm one of those people that loves to really understand how these cool algorithms work. So all this stuff I've done is code I've written from scratch. And you'll find that the GitHub code, it's super simple. So I've avoided using all the useful and cool libraries that are out there that do a much better job, like GenSim and so on, because I think it's a useful thing to do to, if you really want to understand how something works, try and recreate it yourself. So this thing gives me a spectrum like this, which tells me there's some really significant topics in there, and there's a bit of a tail. So it's probably around 1, 2, 3, 4, maybe 10, if I'm being generous. So let's look at the 10 most significant topics. It's probably too small to read, so I can summarize those. Let's look at this one. So this one has words like treaty, Britain, Ottoman, Mesopotamia, resolution. So it's kind of like the history of the Iraq kind of scenario, about some of the treaties, some of the kind of historical kind of demarcations. Let's look at another one. Veterans, mental, medical, inquest, health, reservists, coroners, witness. So that tells you that maybe there's a topic in that text around the veterans and their kind of health after the event, and how they were perhaps treated well or not well. There's an interesting one at the top right there. Telegrams, documents, spellings, redactions, egrams, transcripts. So that seems to be about messaging. The top left one is, I'm running out of time, aren't I? Okay, the point is that this works much better, and it's interesting that you can get out some distinct topics from that text. And the magic is, I didn't read the text, so as a tool for investigating a bunch of evidence or a bunch of text, this idea of extracting topics is really, really handy. I didn't have to read any of that text, and I probably would if I was a researcher, dig into specific areas of it. But this gives me a head start in what are the key topics within a part of text. So I hope that I've given you some intuition around how topic extraction can work. I hope I've inspired maybe some of you to go on and kind of look again afresh at some of the proper libraries like GenSim, but maybe kind of rethink again about some of the assumptions that underlie those libraries. So I think it would be silly to just apply some of these cool library functions to a bunch of text and not really understand what are the limits of that approach. That would be perhaps unwise. If you want to find out more, there's a blog, these slides, there's stuff on GitHub, and if you want to message me, I'm on Twitter. Thank you very much.
We've got some time for some Q&A. Yes, go ahead. Just a couple of slides back.
Yep.
You had some of your topics in red and some in green. Was there a particular reason for that?
Oh, yeah. So it was just for me to say that the green ones were particularly well represented. And some of the red ones were kind of maybe not so well represented. They weren't so clear. It was just a visual aid for myself. And I did a question mark here, so I couldn't really understand what this topic was about. Yeah, so the question was, what do these colours mean? I've coded these, I've coloured these as green and red. It was just for me to say to myself that these are the topics that were really clear from the topic extraction, and the ones that I've coloured red, when I looked at them, they were medium clear, and there's just one that really wasn't clear at all to me.
If you want to go about naming the topics,
Yeah.
How would you start to do it?
So I think that's a really good question. And it's a difficult one because what you're trying to, your topics, like if you looked right at the start with the recipes, cooking, and traffic, automobiles, those words weren't actually in the text. So the recipes, they didn't actually have the word cooking or the word recipe. So your question is, how do we name a topic and potentially the name doesn't even occur? That's an interesting question. I don't know the answer to that. If someone can do that, that would be brilliant. And maybe some of these ideas around using some of the vector models that people have built to say, maybe there's some similarly distant word that's similar to all the other words in the description of a topic. Maybe that's an approach. I haven't really explored it, but it's a good question. This gives you the content of a topic as a linear combination of all those words, but it doesn't give you the actual name of the topic. But that might be a next step to kind of explore. A good question, thank you. Go for it.
So in topic 9,
Yeah.
you can just maybe
Go up, yeah.
the words, yeah. So I can see inquests repeated with different scores, right?
Yeah, one.
Or, yeah, I don't know what the triple is, but is there any way to deal with that kind of like repeated words that are very kind of representing the same thing, but then in such a way that it wouldn't boost to build the topic itself?
Yeah, yeah. So this says inquests. That says inquest. So singular and plural, and that's because in my pipeline, I didn't do what some people do, which is stemming. So if you're a practitioner of text mining, in the steps of cleaning up your text and preparing it, you might stem it or remove plurals of words. You might do that. So your next part of your question was, is there any way of stopping you from overly boosting that? I can only think of no, I can't think of a great way of doing that. I guess if a word appears twice but once in plural, maybe it deserves to be more prominent because it has appeared twice. Can't think of an immediate answer to that. But the reason that's there is I didn't do the stemming or the removal of plurals. And if I was doing this more seriously, then that would be part of my preparation steps.
Any more questions? Thank you.